Welcome to today's lectures. So in this lecture we will study energy level diagrams and some rules of this configuration of the electrons. So let us see first this one. Energy level diagram. What is this energy level diagram? So it is a diagram in which we represent relative energies of the various orbitals in an atom, and it is determined by this n and l. N and l are we already know these are the two quantum numbers. So we will see how this energy are arranged according to the n and l. So we have two cases. One is the monoelectronic atom, second is the multi-electronic atom. So in this case we will study. So in monoelectronic atom or ions, we have hydrogen, helium plus, lithium dipositive, beryllium tripositive. So all substances belong to the same energy level. So if the same energy level, they have same energy. In these cases, suppose we are taking 1s 2s 2p. So here 2s 2p both have same energy, and here 3s 3p 3d, here they have also same energy. 4s 4p equal to, but it is increasing order. So one is lesser than 2s, but these are equal to each other, but they are equal to each other. These three orbitals are, these four substances are equal to each other, these five substances are equal to each other. So like this, here I have drawn one diagram, you can see here. So this is 1s energy level, both are equal, here both are equal, here both are equal. So this is easy to understand. But this does not happen. Does not happen in multi-electron atom. So see in this how it differs from the previous one. Here exact value of energy level cannot be calculated. Why? Because it is decided by so many factors like nuclear attractions, electronic repulsion, so due to which energy cannot be properly decided. So what happens? And these approximate values are calculated by observing spectral lines. So here you can see the energy level in the case of hydrogen or hydrogen-like atoms are same to each other, but here we can see 1s is down here, 2s is up, but 2p is this side. Okay, means 2p here we can see all are equal to each other. Okay, 2p cases, but there is difference between 2s and 2p. So here 2s is lesser than the 2p, here 3s is lesser than the 3p. You can see here 4s is lesser than 3. So here things are different. Okay, but here all are same. So this is very important because in entrance examination they are asking these small questions. Main features of this diagram is that you can see already we can conclude from this examples diagrams. 3s 3p and 3d poses different energies, though they belong to the same energy level. We have seen. So we can see one diagram once again. 3s 3p and 3 both have different energies. Then again, energy of s is smaller than the p, smaller than the d, smaller than f is the largest energy. So like this, if you take 4 subcells in which 4f has greater energy than the 4s. Again 2px is equal to 2 pi p and 2pz. Among the same energy levels, they can be equal to each other. Similarly, for the d orbitals, they have same energy when the d orbitals are present in absence of magnetic field. If you put in magnetic field, then again they having a triplet orbitals and doublet orbital that we have seen in previous lectures. So it should be in absence of magnetic field. Keep in mind, this is important point. We will study in coming chapters how this is split into d orbitals are split into magnetic field. Now increasing orders of energy sublevels. So these are following this order, n plus l rule. We will going to study next topic what is n plus l rule. So if you add n plus l rule, this all energies are electronic subcell energies are increasing like this only. 1s 2s 2p 3s 3p 4s 3d, then 4p 4s. You can see here 4s and 3d. So why 4s is lesser than 3d? We will study this one. See here, shell having lower n plus l has this n plus l rule. Already I have given here also. So if the shell has lower n plus l, like 4s n plus l, 4 n means here 4, l means 0, so 4. If you take 3d, n is 3, here d is 2, 3 plus 2 5. So 5 is lower than the 4. So this has lower energy, this has higher energy. Similarly 5 is 4d, so 5 plus 0 5, 4 plus 2 6. So 5 is lower, definitely energy of the 5s orbital is lesser than the 4d. So this is the highest energy. That's why in case of, you can see here 5s and 4d. Here you can see clearly over here you can see here, and in 4s and 3d we can see this side also. It is very clear. If the two cells having the same n plus n, suppose Then subcell with the lower value of n has lower energy. Suppose 4f and 5d. Here how we can decide? So n plus l is 7 and here n plus l is 7. Then the lower value of n has lower energy. So this is lower n. So this having lower energy is higher energy. 4f is lower energy, 5d is higher energy. Similarly, it will happen here also. 4s and 3p. You can see 4 is there. So 3p has lower energy because it has 3 and is higher energy. So this is the basically differentiation of different energies of the sublevel according to the n plus l rule. Now we'll see electronic configuration of atoms. What is this one? It is a distribution of the electrons in various energy shells and orbitals in an atom in the ground state. It is written in the form of NLX. What is N? N is the principal quantum number. L we know subcell azimuthal quantum number. X is the number of electrons present in the subcell. So NLX is written like this one. We can also write this whole NLX in terms of orbital diagrams also. Configuration. So like suppose hydrogen has 1s. So 1s means 1 arrow, 1s2. So it will be, suppose helium is 1s2. So we can write a 2 arrow. This is your 1s1. We can write circle also. 2s2. Suppose this one. So in circle also. Like this also we can write in this form also. So there are 3 forms. Anyone we can write it. For exact distribution of electrons in various energy cells of different atoms, so following rules are followed. So to fill this electron in the configuration, these are the rules. According to these rules, we can fill inside the orbitals. That is a square shape, circle shapes, like that. So first rule is Aufbau rule. What is Aufbau rule? So this is a subcell with minimum energy is filled up first, and when this attains maximum quota of electrons, the next subcell of higher energy starts filling. So it will be filling. So you write here starts filling, and it is determined with the help of n plus l rule that we have seen in previous before that is also n plus l, how we are filling the electrons. What is Aufbau? Aufbau is a German word. It is a German word, not an English word. So its meaning is building up, means increasing. Something is increasing. So here energy is increasing. So n plus l, we have seen this rule, so there is no need of writing. I have written just for the revision purpose. So n plus l means subcell with lowest value will be filled up first. When the 2 or more cells having a same n plus l value, then the subcell with the lowest value of l is filled up with the first. So this we have seen the previous examples. Here the this diagram is given. In this diagram we can easily understand. So you can see here 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4df. So here diagram is given. N2, N3 all are given. These are the different orbits energy cells. You see n plus l rule. If you see n plus l, this becomes 1, this is 2, this is 3, 2 plus 0, 2, 2 plus 1, 3. Here 3 plus 0, s is 0, 3 plus 0 will be 3, 3, here p is 1, 3 plus 1, 4, here 3 is there, d value of d is 2. Here if you take 4f, 4 plus 3 is 7. So here 1, this is a lower value, so electron will fill first, then 2, then 3. After 3, we will go this side. And here both 3 is there, so here we have lower n value, so this will be filled first, then this will be filled first. So like this 3p and 4s, this will be filled first, then this will be filled first. Here all have same 5, here all have 6, here all will be same. So first electron will fill this one because it has lower energy, then this one, 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 this one, this one. So like this electron is filled up. So here I have drawn this sequence 1s2, 2s2, 3s2, 2p, 3, 3, like this one, 4d, 4p, 5s. This is the 5s. Then 4d, 5p, 6s, 6s, f4f, 4d, 6s, 7s, 5f, 6d, 7p and 8s. So this is the sequence of filling the electrons according to the Aufbau rule. Now next rule is a Pauli exclusion principle. So in this it states that an orbital each have maximum 2 electrons with opposite spins, and no 2 electrons in an atom can have the same set of all the 4 quantum numbers. So electrons should have 2 opposite spins. So this is the important point. So we can see this diagram. Opposite spin, we have seen it. Opposite spin means, suppose this is the square shape, so we have to write like this one. One is the clockwise, other will be anti-clockwise. So this is the correct method. if you're writing like this one, both are parallel like this one, this will be incorrect method. So this is wrong. Let us see one example. Nitrogen, this I have given one example, 1s2, 2s2, 2px1, 2py1, 2pz1. So filling will be electron. So here 2 electron, 1 1 1 electron, and is very easy. 1 2 2, L will be here for 0 0, S S 0, P is 1 1 1, M is plus 1 minus 1 0, and S will be here plus half, minus half, plus half, or minus half. This will be plus half, plus half, plus half, or minus half, minus half, minus half. Anything you can take it. This is the way of filling the Pauli exclusion principle. After this, if you are writing 2 4, then it will go here. Hund's rule. What is the Hund's rule of maximum multiplicity? So it is the pairing of electron in degenerate orbitals of a subcell is not possible until all the available orbitals of a given set contains one electron, as well as half-filled orbitals have same spin electrons. What is the meaning? Pairing will not take place. Why? Unless all the subcells is filled up with the half electron or singly occupied. You can see here carbon is there, 2s2, 1s2, 2s2, 2 picks, 6 is the atomic numbers. You can see here. So if you take the first electron, it goes here. For I am taking 2 subcell. The 2 subcell contains 2 energy cells. That is the second orbit contains 4 electrons. So one is 2s2, one is 2p2. So let us take 2p2. So in 2p2, what will happen? So here first electron will go like this one. Okay. So this is 2p2. So here we can't write. This is wrong. Okay. This is also wrong. Okay. So first will be here 2p2. Then here 2p2, 1. First one. Then second here. Then third is absent. So 1, 2, and this will be blanked. Okay. The third is absent here. So this is blanked. So we can write here n equal to this 2, L equal to 1. Why? Because P is there. M equal to minus half. This is minus 1. This is the 0. This is the plus 1. But plus 1, there is no electron is there. So in the case you can write any one. So if there is plus 1 third orbital, so here it will be spin will be not half. This will be 0 or 0, because this is the counted for the this one only 2 electrons. So this will be 0 or 0. So this is the correct answer. I have made one mistake, so just correct it. Okay, because Hund's rule says that suppose you take nitrogen. So nitrogen contains 1s2, 2s2, and 2p3. Or you take better oxygen. Oxygen means 2p4. If you take 2p4, so here how electron is filled up? The first electron 2p1, then second, then third, then fourth. So like this is electron is filled up. The fourth electron is filled, then this is following the Pauli exclusive principle. Then before that Hund's rule is filled. Means first Hund's rule is followed by Pauli rules is followed. There are some exceptional configurations you can see here. And this is chromium, copper, niobium, molybdenum, ruthenium. So these are you can see. Actual configuration is 3d 5 4s1, but expected configuration is 3d 4 4s2. This should be according to the n plus L rule. This is also according to the n plus L rule, but we are getting 3d10 4s1, means one electron from the 4s is jumped to 3d10. Now why it happens? So this is explained on the basis of half filled or completely filled orbitals. So when the orbitals be d5, d10, f7, f14, then this will be more stable. So to maintain the stability, this electron is jumping from the 4s1 to 3d10. So let us see how. Extra stability of the half filled and completely filled orbitals is due to two reasons. One is the symmetrical distribution of electrons. So here electrons in the same subcell have equal energy but different spatial distributions. So consequently their shielding of one another relatively small, and electrons are more strongly attracted by the nucleus. This brings stability. So let us take example of chromium. So in chromium expected configuration as 3d 4 and 4s2. So this is the expected 3d 4 and 4s2 because the atomic number is 24. So this will be 20, this is 24. So this is expected, but we are getting like this one. Means this is occupied, one electron is shifting from here to here, like this one. Similarly in copper, I have seen the previous page 29. So this is 3d9, 4s2. Okay, this is 4s2. So here we are getting how much? This is expected, but we are getting like this configuration. Means one electron from the shifting from this 4s2 to this one. So we will get here 4s1. This is the 1. Here will be 1. And this 310. So this is the more stable orbitals than this one. So this is one of the reasons for the stability, that is the symmetrical distribution of electron. Second reason is exchange of energy. So if the exchange of energy will be more, then this is bringing the more stability. What happen in exchange energy? Energy released during this exchange and brings the stability. Number of exchanges that occur is maximum when all the orbitals of a substance are singly occupied or doubly occupied. So as a result, exchange energy is maximum and it causes stability. See chromium. Chromium we know it's 24. So actually this one 3d4 4s2. See in 3d 4 4s2, why there is less in exchange of energy? Exchange energy means this is the 4 electrons. So these 4 electrons are exchanging energy. So this is exchanging with this one. This is, I am talking about this electron. This can exchange with this one, with this one, with this one, with this one, with 4 exchanges. Now take the second electron. This can exchange with this one and this one, 2 exchanges. And third electron can exchange with only this one. So total exchange will be 3 plus 2 plus 1, that is 6. Now take in case of 3d5 and 4s1. So in 3d5 4s1, what will happen? This is 3d5 and 4s1. So 3d5 first will exchange with this one, this one, this one, this one. So 4 exchanges possible. Now you take the second electron. This can exchange with the 4 types. 3 exchange possible. You take third one, 2 exchange possible. You take fourth one, 1 exchange possible. So total exchange will be 4 plus 2 plus 3 plus 1, that is 10. So here we have 6 exchanges. Here we have 10 exchanges. 10 exchanges is more stable than the 6 exchanges. So this is more stable than the 6th one. Now let us see some configurations. Examples. Write electronic configuration all electrons sodium which have 11 electrons. So this is the configuration of sodium: 1s2, 2s2, 2p6 and 3s1. So here we can see this is following the Pauli exclusion principles, Aufbau rule, Hertz rule, everything we are following. So here this is according to the Aufbau rule. We have arranged 1s2, 2s2, 2p6, 3s2. Now we see how Pauli rules and the Hertz rules are followed. Pauli principles and Hertz rules are followed. So this is the first electron, second electron, third, fourth, fifth. I have given the name like 6, 7, 8. Now LM and LMN, you can see the quantum numbers. We are drawing the configuration as well as quantum number of each electron. So for 1s electron, we can write it. This is the 1, the S0. For S, L will be 0, M will be 0. So first electron will be plus half or minus half. Now come for second electron. For second electron, since it is s orbital, so this 3 will be same, but second electron will be minus half. So we can see this is opposite spin. So this is one orbital, this is second orbital. You can write this one or this one. So we are following the Pauli principle. Now come to second, same thing is there. 2, 0, 0, here will be plus half, minus half, but in case of second, 3 will be same, fourth will not be same. Because this is minus half. If you are writing this is minus half, this will be plus half. So either you write this one or this one. Come to fifth one. Fifth one is P. P is there. P we have 6 electrons, 3 orbitals. So 2, 1. So this will be same. N and L will be same, but N will change. So first electron will go Px. This is the Px. Okay. Suppose this is the Px. This will be your Py. This is your. Suppose this is Pz, and this is your Py. So first we take this one or this one. So here we are following the Hertz rule. Okay, it's clear. We are following the Hertz rule. After that, Pauli principles. So Pauli principles, after filling this one, so here this 8th electron will go for in the 6th orbital. Sorry, this one. Which orbital? 2p orbital, first orbital, 8th electron. So this is again Px. This is again Pz. This is again Py. So this will be minus half, minus half, minus half. If you are taking all 3 plus half, so this will be all minus half. So up to 10 electron will be filled up. So 2p is filled up. Now next orbital, next electron will go in next s orbital. So 11th electron will be 3s1. So write 3, 0, 0. This will be plus half or minus half. So in this way, electron is filled up in the orbitals. Now let us see some examples of ions. So this will be easy to understand because in examination these questions are normally asked. Calcium dipositive means it has 2 less electrons. So we like configuration 1s2, 2s2, 2p6, 3s2, 3p6 and 4s0. This you can write or you cannot write. It depends on you. So 4s0 means no electron. If you write 4s2 means this will be calcium ion. So here I have given this example also. Here 4s2 is there. You can see clearly. Similarly, iron 2 plus 26 the configuration. So 1s2 26 means 26 minus 2 24. So we will see these electrons are 24. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So here we can also see 1 means K cell contain 2 electrons. This is the K, this is the L and this is the M. So K contains 2, L contains 6 plus 2, 8 electrons and M contains how many electrons? So 6 plus 6, 12 plus 2, 14 electrons are there. Here we can also write this is the K, this is the L and this is the M and this is the N is 0. So here we can write 2 electrons, this will be 8 electrons, this will be your 8 electrons. Similarly you can see here this will be your 2 electrons, this will be your 8 electrons, L, KL, this will be your M. M means 6 plus 2, 8 plus 5, 13 electrons. This is the M. So in this way we can write KLM how many electrons are present. Cl you can see here this is 2 electrons, this will be your again 8 electrons, 2 electrons, this will be your 8 electrons, 2, 8, 8. KLM. Here also 2 minus means 8 plus 2, 10 electrons. So 4 plus 4, 2 and plus here this will be 6. It is by mistake 6. Okay. So this is a K and this is your L. So electrons will be 2 and 8. 2, 8, 10 electrons. So we can see calcium we have seen it. So in this way electron is filled and we can write their configurations shell wise or subshell wise. We can write any way. If you know this proper filling, we can write any examples.